We are a team of colleagues at Monash University in Melbourne, Australia and ETH Zurich in Switzerland. Together we show our research on cartographic relief shading with neural networks. This is an excellent example of a topographic map created by SwissTopo, the Swiss National Mapping Agency. All map elements have been carefully optimized for readability. However, the map in this form does not clearly show the third dimension of the terrain. The map contains contour lines, but extracting elevation from contour lines is tedious and difficult. When a shaded relief image is added, the shape of the terrain is very clearly visualized. We can immediately distinguish between low valleys and high mountains, and we can also identify small details, for example smaller valleys or landslides. Shaded relief is very effective at different map scales. Here we see a detailed map at the large scale showing a small section of the Jura Mountains in Switzerland. Drawing shaded relief requires specialized expertise. Here is a time-lapse showing cartographer Sarah Bell drawing a shaded relief image. She uses pencils, but even when using digital image editing tools, creating high-quality shaded relief is immensely labor-intensive. Experts at SwissTopo have perfectioned the art of cartographic relief shading. Here is a SwissTopo cartographer spraying a shaded relief with an analog airbrush. This results in outstanding shaded relief images, such as this piece of art that very clearly shows the structure of the main landforms. Our goal was to develop a digital method that creates shaded relief images of similar quality from digital elevation models. We developed a neural network that improves on existing algorithms. Here is an example output of our neural network. We trained the network with a manual relief shading of Switzerland and then applied the network to a digital elevation model of the Caucasus Mountains. In our presentation, we will first look at design principles that cartographers apply when manually shading a terrain. Then we will discuss the architecture of our neural network and describe how we trained the network. Then we will show how the shading can be controlled to adapt results to the characteristics of the terrain. And finally, we will show results of an evaluation that we conducted with expert cartographers.
Cartographers have developed a series of design principles for creating effective shaded relief images. We start with briefly reviewing these principles because they guided our research. This is again the manual shading produced by Eduard Imhof and Heinz Leutzinger. Let's analyze what design principles they used when creating it. The general direction of illumination is from the top left. This reduces the chances of relief inversion. Relief inversion may occur when the terrain is illuminated from the bottom. With relief inversion, mountains are perceived as valleys and valleys are perceived as mountains. However, with an illumination strictly coming from the top left, not all terrain forms are illuminated in the best way. This mountain is a good example. Its main ridge is in northwestern direction, which aligns with the top left illumination direction. As a result, both sides of this mountain would receive the same amount of illumination, and both sides would be shown with the same gray value. This major mountain ridge would be barely noticeable. To avoid this, the cartographers adjusted the direction of illumination. This is the local direction of illumination used for drawing this shading. So instead of this regular top left illumination, the cartographers adjust illumination throughout to show each landform with the best light. Another important design principle is highlighting of large landforms. The terrain is structured in major illuminated slopes and also shaded slopes. Illuminated slopes are brightened and the shaded slopes are darkened. This results in this clear structure where mountains are grouped and valleys are clearly visible. So, in essence, the brightness of an individual pixel is determined by shape and size of the landform of which it is part of. Generalization is the abstraction of information with scale. Here is an excellent example showing the Aletsch Glacier in the Swiss Alps. The characteristic shapes of the landforms are shown at all scales, but the level of detail gradually changes with scale.
We experimented with different neural network concepts such as encoder-decoder networks and neural style transfer. Finally, we found that the unit architecture shows the most promising results. Originally, the unit was introduced by Ronneberger et al. In 2015 for semantic segmentation. Here you can see what our specific version of the unit for terrain shading looks like. In essence, the unit maps a tile of a digital elevation model to a shaded relief tile covering the same area. This is being carried out by a sequence of convolutional layers that gradually modulate the input image until the output image is obtained. In the final layer, a cropping operation is performed, effectively reducing the size of the tile for which the predictions have to be made. This is necessary, as the correct grayscale values of the relief shading tile are highly context-dependent. For the cropped pixels, it is assumed that not enough context information is present to enable the neural network to make correct predictions. A sequence of convolutional layers alone is not able to capture enough context to make informed predictions. Hence, convolutional neural networks typically also employ pooling layers to gradually generate compact representations of the input image. The stepwise combination of pooling and convolutional layers make up the so-called contracting path of the unit. The feature representation needs to be scaled back to the dimensions of the target tile. This is being carried out by the expanding path, which employs several convolutional and deconvolutional layers to gradually increase the spatial dimensions again. Constructing a relief shading tile from a compact representation often lacks fine-grained local information in the final image. By combining activation matrices of the contracting path with the matching activation matrices of the expanding path, it is possible for the network to analyze both high-level and low-level information. This results in locally more accurate relief shadings.
We trained various networks with shaded relief images created for maps at different scales. For example, here we see the 78 sheets of the Swiss Topo Map series at a scale of 1 to 50,000 that we used for training. Here is a section of this shaded relief. For training the networks, we used standard GPUs. We used images and elevation models that measured up to 16,000 times 10,000 pixels. We ran up to 5,000 epochs, which required up to 5 hours of training.
The neural networks for relief shading do not have parameters that can be tuned directly, but we can adjust how we use the neural network to control the output shaded relief. When computing a shaded relief, a trained neural network reads an elevation model, such as this one, and computes a shaded relief image. It applies the light direction that it learned during training. Sometimes it's useful to adjust the direction of illumination, for example, when we want to imitate the natural southern illumination direction on the northern hemisphere. This can be achieved by first rotating the elevation model, then shading the rotated elevation model, and then rotating the shading back to the original orientation. The result is a shaded relief with southern illumination. Of course, we can use any angle of rotation. We train neural networks with elevation models and shadings of Switzerland. Here is what happens when we apply one of our networks to the lowlands of northern Poland. This rather flat lowland is shown almost like an alpine landscape, with strong contrast and sharp edges. This happens because the elevations of this lowland are scaled to the elevation range of Switzerland. Here we only use the lower 20% of the possible elevation range. As you can see, contrast in this shaded relief is reduced, and the lowlands are more accurately portrayed. We can control this level of generalization with two methods. Here, we simply downsample the cell size of the elevation model and apply the same neural network. The network learned to retain and accentuate sharp mountain ridges, so the shaded terrain does not appear blurred, even with the larger cell size. Here is a second method for generalization. We trained 3 neural networks with elevation models with different cell sizes. The 3 images here were created by applying the 3 neural networks to the same elevation model. The neural network that created the image on the left was trained with a low-resolution elevation model. It learned to retain as many details as possible. The effect is that the shaded relief shows many details. The neural network that created the image on the right was trained with a high-resolution elevation model. It learned to discard information and only retain the most essential shapes. The effect is that the shaded relief only shows the most important landforms.
To evaluate our results, we conducted a study. 18 relief shading experts participated. We selected 10 high-quality shaded relief images that were produced manually. We then created corresponding shaded relief images of the same area with our neural networks. The experts were asked to rate the images of each pair. These are the 10 pairs of relief shadings. Let's have a closer look at what the experts thought about them. For each pair, we asked them to indicate which of the two shaded reliefs is better for a topographic map. We did not tell them which image was created with a neural network. For 5 of the 10 pairs, the experts preferred the neural network shading. Here's an example. On the left is the preferred neural network shading, and on the right is the manual shading. For each pair, we asked experts to identify the shading that was aesthetically more pleasing. The answers were similar to the overall preference. Here is an example, where the experts found the neural network shading on the right to be more pleasing than the manual shading on the left. For each pair, we also asked experts to identify the shading that was produced manually. In general, they found this difficult. 3 pairs were particularly difficult. Here's the one of these examples. The neural network shading is on the right.
We now come to the conclusion of our presentation. We have proposed a neural network architecture that can create high-quality shaded relief. An advantage compared to other digital shading algorithms is the consistent and visually pleasant generalization of terrain. Another advantage is the direction of illumination is adjusted to highlight important landforms. In summary, we hope to contribute to the curation of cartographic relief shading and bring high-quality shaded relief to the reach of modern mapmakers. We would like to thank the National Geographic Society for supporting this research project with an exploration grant. We also thank the 18 relief shading experts who participated in the study and the anonymous reviewers for their comments and suggestions.